Hello, this is Dr. David Lupkeman. In this video, I will show you how to perform fault analysis on a basic power system model, as shown here on the left, in order to calculate the transit fault current characteristics, as shown here on the right. I will start by deriving a closed-form equation for a single-phase fault. Then I will go over a Python programming example for calculating and plotting the fault current. The presentation notes with Python programming examples are in Jupyter Notebook format. Jupyter Notebook and Jupyter Lab are popular open source data analytics tools developed by Project Jupyter. I am using the newer Jupyter Lab tool, which supports multiple windows, for this particular presentation. Jupyter Notebook is the original single window environment. The notebook is broken down into cells, where I have three different types of cells here. The markdown cell, which I use for text with figures or equations in LaTeX format. Code cell with Python example you can execute with Shift-Enter. And the output cell, which contains the code result. You are encouraged to download notebook material from the GitHub site so you can follow along. The current link to the site is provided in the video description. Note that Jupyter Notebook files have the IPYNB extension. The PSCAD Benchmark example has the PSCX file extension. And graphic files used in the notebook are stored in the images directory. You have the following options to view the notebook material. Option 1 is to download the notebook IPYNB file with image files and run Jupyter Notebook or Jupyter Lab on your local computer. You can download Jupyter Lab or Notebook from the Jupyter project site. Or you could use the Anaconda Data Analytics environment, which includes an instance of either Jupyter Lab or Notebook. Note also that Microsoft Visual Studio Code also has a Jupyter Notebook extension which can be used to view, edit, and run the notebook file. In this case, use the VS Code version on GitHub. Option 2 is to use the Google Colab version provided on GitHub so you can run the notebook on a Google Cloud server. This way you don't have to download Jupyter Lab or Notebook. You can just click on the file in GitHub and hit the hot link at the top of the page. This will then take you to your Google Drive directory with a copy of this notebook open. Note that the images are embedded into this notebook instead of having them in a separate images directory. Option 3 is to download the Python code version provided so you can execute this notebook in a Python coding environment. This shows the file in Microsoft Visual Code. Note that all markdown text and equations in this case have been converted into comments. Finally, option 4 is to download and view the PDF version. Links to tool sites referenced above are provided in the video description. The scenario we will be analyzing is a single source radial system with fault location as shown here. In this scenario, we have a power system with voltage source and source impedance C, a single phase fault modeled by an ideal switch, a circuit breaker set up to clear a fault, and finally, a relay that monitors the breaker current, detects the fault, and sends open and close signals to the breaker. An example fault measurement for a medium voltage circuit is shown here. Note that we have a pre-fault load current, a peak instantaneous current magnitude, which is typically greater than the interrupting current, and finally, a steady state current to be interrupted by the protection device. We want to be able to predict these fault current characteristics based on the circuit model shown earlier. The equivalent RL circuit model based on our fault scenario is shown here. Note that this calculation is based on a Thevenin equivalent circuit as seen from the point of the fault. We're going to have an equivalent voltage that corresponds to square root of 2 Vm sine omega t plus theta, where Vm is the per phase nominal voltage RMS magnitude, and theta is the point and wave angle for the fault, which we'll be talking about later. R and L are self-impedances for the faulted phase. These are not positive sequence values, since we are only considering a single-phase fault. We will initially consider just a no-load case, so this pre-fault current is going to be 0 for this circuit, and we'll be formatting these equations assuming the fault occurs at time t equal to 0 to simplify our analysis. Finally, since the inductor current cannot change instantaneously at the time of switching, and we have no pre-fault load current, then this initial value for the current at time equals 0 is just simply going to be equal to 0. When the switch modeling the fault closes at time equal to 0, then we have a basic loop circuit to solve in order to get the current. Current is related to the source voltage by the ordinary differential equation shown below, where LdIdt plus Ri is equal to the source voltage square root of 2 times Vm times sine with argument omega t plus theta. Associated with this equation is a boundary condition that the current at time equals 0 is equal to 0. Note in this formulation the point on wave angle, theta, is adjusted to give us the desired voltage at time equal to 0. So for example, a fault occurring during a point on wave equal to the peak voltage has theta equal to 90 degrees. For this linear RL circuit, the current solution has a steady state component and a transit component that when added up gives us the total current. And so our fault current has the form of current equal to ISS plus ITR, where the steady state component with the subscript SS corresponds to what occurs in steady state due to the sinusoidal forcing function. We will look at how to get this first. The transit component, which I'm denoting by the subscript TR, is then obtained by analyzing the natural response of this RL circuit without a forcing function and also factoring in the boundary condition. To obtain the steady state component of the solution, we need to perform a phasor analysis using the circuit shown here and convert the result back to the time domain. Note we have replaced the time domain source by its phasor equivalent with magnitude Vm and angle theta. Also, the resistance and inductance has been replaced by the phasor impedances R and J omega L. The circuit impedance can be represented in polar form by finding the magnitude and angle as shown here, where the magnitude of the impedance is the square root of R squared plus omega L squared, and phi is the arctangent of omega L divided by R. We obtain the phasor current by dividing the phasor voltage by the complex impedance to get the magnitude and angle for the voltage. Finally, we convert the phasor current to the time domain by multiplying the magnitude by the square root of 2 and then converting the angle portion into a sinusoid which has an argument of omega t plus theta minus phi. This plot shows an example steady state fault current. Note how this waveform is symmetrical about the y-axis, which is why it is sometimes referred to as a symmetrical current component. The RMS magnitude of this current is typically used to determine the interrupting capability required of the circuit breaker, and it's also used for protection coordination with upstream and downstream protection devices. The steady-state current solution is still incomplete though, since we have a boundary condition of current equal to 0 at time equal to 0. Looking at this steady-state component plot, we see an instantaneous jump in the current when the fault is applied. This is not possible since current cannot change instantaneously in the series inductance. We need to model the transition from a steady-state pre-fault circuit to a steady-state faulted circuit by including an additional transit component. The transit component of the solution is found by solving the circuit shown here. This is similar to the circuit we use for steady state. Although the circuit has no forcing function, it does have a non-zero initial current. When we write the loop equation for this transit circuit, we get the differential equation LdIdt plus Ri is equal to 0, 0 because there is no forcing function. The formula of the solution for current is an exponential where the current is equal to AE with argument st, where E is the exponential function, A is going to be a function of the boundary condition, and S is a complex number that we still need to solve for. If we substitute I equal to AEST into this differential equation, note that the first derivative of current is simply S times the original current function. To solve for S, we divide both sides of equality by AEST and then get what is referred to as the characteristic equation. For this RL series circuit, S is equal to minus R over L, which in this case is a real number. Substituting for S, we see that the transient component of current is equal to AE with argument minus R over L times T. Now, if we add the steady state and transient components, we get the complete current solution shown here. We will get constant A by applying the initial current at time equals 0. Note that the exponential term adds an exponentially decaying DC component to the steady state solution. Due to the series inductance, the current cannot change instantaneously due to the fault switching event. So we have this condition that current right before the fault has to be equal to the current right after the fault. In this case, both are equal to 0 because we were just looking at a no-load condition. To find A, we take our total current solution and set T equal to 0 and apply the known current at time equal to 0, which in this case is 0. We can then find the expression for A. Substituting for A, we get the final solution for current that we will be using in our Python simulation. Again, note that this transit total current solution includes an exponentially decaying DC component. In this presentation, I have been scrolling through the material in my Jupyter notebook file and reviewing the relevant circuit theory needed to derive a closed-form solution for the fault current. Now that we have the solution shown in equation 15, we can write a Python program to calculate and plot the transit response. The code for doing this is shown in this code cell. I execute this code block by typing Shift-Enter. The results are then shown in the output cell that follows. Let me jump out of the slide presentation mode and just focus on the Python code cell for now. And we're going to go ahead and start by reviewing the program organization. At the top of the program, we start by loading in the Python libraries. Note we are making use of the standard Python math library as well as a library that emulates MATLAB plotting calls. For the matplot lib call that we'll use, PLT is going to be the prefix for the function calls. Next, we have the definitions for the current versus time and the plot current components functions, which I'll cover later. At the beginning of the program, I define the variables. You need to set parameters for the RMS voltage magnitude Vm, the impedances R and X, system frequency F, and the point on wave angle theta. I've gone ahead and inserted typical data. Normally, reactance X is the known parameter, and you need to convert to inductance as shown here. Once these values are defined, I print them out again in a slightly different form in the output, so I will have them available for the benchmark case we'll be reviewing after this code example. Next, we compute values for current as a function of time. I will use conventional Python lists in this example and start out by setting up solution time points in list called t-values. I start by initializing t-values as an empty list and then append time points one by one using a for loop. So this list grows by one value per iteration. I do this for a list size corresponding to 1024 samples per electrical cycle for a duration of 6 cycles. The time points have a discrete resolution of 1 over f divided by 1024 seconds. If I wanted to be a more efficient programmer, I could use Python list comprehension instead of the for loop, as shown in this comment below. Since I want to plot not only the total fault current, but the steady state and DC offset components, I'll go ahead and set up 3 lists. I also have a voltage list for the plotting. Next, I call the current versus time function in a for loop to populate these lists. I do this for times corresponding to the time values already in the list t-values. If I go to the top of the program and look at the function current versus time, you can see that I only pass a single time value in the simulation parameters. We then compute the source voltage, a current magnitude intermediate term, and finally the steady state and the transient response components. The function finally returns the total current, steady state component, transient component, and source voltage all evaluated at time t. There are a number of different ways we could have computed the current values, but I wanted to keep this example fairly simple. For example, we could have used list comprehension as shown in the comments to eliminate this for loop. Another option would be to use the Python NumPy library to streamline these calculations, but this improvement will be the subject of a separate follow-up video. Once we have the current and voltage list with our data, then we can call the plotting function plot current components. We pass the time, current, and voltage list as inputs to this function. In the plotting function, I have set up two different plots. The first is voltage only, and the second has the three currents, all plotted with time on the x-axis. Fig points to the figure object, while ax refers to an array of axes objects. And so ax with argument 0 refers to the voltage plot versus time, where I've defined a plot color, plot label, and y-axis label. And ax with argument 1 refers to the currents plotted versus time, and we have plot calls for iTotal, ISS, and ITR. In this section, I also label the x-axis for the time points. When we look at the resulting plots, you can now see for the input parameters how by adding the DC transit component in green to the steady state current component in red gives us the total transit current with an offset that decays with time, where this particular plot is in blue. Finally, I find the peak current magnitudes for the total current and the steady state current. Then I use these two values to get a ratio, which I call asim underscore isim. This is the ratio of the total asymmetrical current to the symmetrical current. This ratio is a multiplier that is used to tell us how much higher the withstand current for the circuit breaker needs to be with respect to the interrupting current. The reason I'm doing this is I want to be able to show how this ratio changes for adjustments in the point on wave angle theta. The base case that I have here has theta equal to 0, and for this I get a ratio of 1.55. But if I change this to 90 degrees, this is the same as 2 pi over 4, then we see that the peak value drops off quite a bit with a ratio of 1.08. Using the transient fault current solution in simulation, I have shown how we can quantify the asymmetrical addition to the symmetrical steady-state fault current. This DC offset needs to be factored into circuit breaker instantaneous withstand ratings. Normally in the time it takes for the relay to send a trip signal and then have the circuit breaker operate, this DC offset current component will have decayed out. So the circuit breaker just needs to interrupt the steady-state symmetrical component. To conclude this simulation section, let's look at a table showing the impact of adjusting the point on wave angle theta. One can see that the DC offset changes significantly with theta, varying from about unity to 1.55. The worst case occurs when theta is equal to 0 or 180 degrees. This corresponds to having a complete half cycle of source voltage charge a series inductance to its peak possible value for these circuit conditions. In this section, we will benchmark the Python simulation program using a commercial transit analysis program. Specifically, we will be using PSCAD Free version 5, which you can download at the highlighted link. The PSCAD study file developed for this benchmark is available on the GitHub site, referenced in the video description. When you open the project file, you can see the circuit model and plots. Let's go ahead and zoom in on the circuit. If we double-click on the source model and look at the source initial values, we can see the setting for voltage per phase RMS magnitude, frequency, and point on wave angle. Double-clicking on the resistance and reactance in the circuit model, we can also see the value set up that I printed in the Python simulation code for future reference. The circuit breaker is initially open, as indicated in green, and set to close via the timed breaker logic at time equals 0. Note I have also set up plot channels to capture the source voltage and fault current. Now let us run the simulation and look at the transit results. Note the circuit breaker modeling the fault transition changes color from green to red to indicate closure. If I have the plot set up with the crosshairs to view simulation results, I can see that the peak asymmetrical current is 7,442 amperes. Looking at the last cycle, I can see the symmetrical current is 4,804 amperes. So in summary, for a single-phase fault modeled by a Thevenin equivalent RL impedance and voltage source defined by square root of 2 times Vm times sine with argument of omega t plus theta, we have an expression for the fault current that consists of two parts: a steady-state symmetrical component, which is basically what we get from phasor analysis, and a DC term that decays exponentially with time. Both terms put together gives us the total asymmetrical current, which we can see satisfies a boundary condition of zero current at time equal to 0. The impact of this DC component is that it puts additional stress on the circuit breaker during the first cycle of the fault. If you have any questions on this material or the associated Jupyter Notebook content on GitHub, please post these in the comments section of this video. To watch more content like this, please consider subscribing.